Okay, so grab a seat, everyone. It's the last opportunity to do so. So the next session, Catherine has kindly organized, but I decided it was a bit harsh on her to chair her own session. So she's speaking today. She's done a lot of work on the stochastic block model. I think I know at least the 2 GRSSB papers that are really nice. And I'm very happy to have her kick off this session. Thank you.
Thank you, Sophia. So first, I'd like to thank the organizers and really especially Sophia, who did such a great job in organizing this program and this week. So many thanks, Sophia. So I'm sorry, I'm going to talk about the stochastic block model again. So maybe it's a bit too much, but it will be my very biased point of view on the statistical issues on this model. So I've been working on this model for many years now. Maybe I should think of doing something else, I don't know. But okay, I still have some questions that I want to solve, and I'll tell you about that and about the things that have been solved already. So first of all, I'd like to just say a few words about the type of networks I've been interested in, at least in the last few months. These were mainly contact networks. So there are a lot of data about animal or human contact networks that are built from either field of observations of associations between the individuals, or a lot of data also with sensor-based measurement. So you put a chip on an individual and you can track him with a GPS. And when two individuals are very close to each other, you decide that there's an interaction between those two. You also encounter data made by trapping events. And some questions that people can ask on this data set are those ones. So for instance, is there a social structure that we can observe among these individuals? Can we understand if there is a peculiar non-random mixing of these individuals that would be a sign for some kind of social organization? That's one of the questions. How does this vary with other factors, like, for instance, the breeding season, if you're studying animals, or the seasonal changes, the response to stress, etc.? And can you handle also on these animal data sets, very often you have arrival or departure of a peculiar individual, because either he will be dead, or if it's a new season, maybe there are new individuals that are born in your data set. So you need to handle that in dynamic settings. Other questions concern, for instance, the prediction of infectious disease, or do they spread among your network? And, well, other questions like that. I've been interested in modeling heterogeneity for a while now, because these data sets are obviously very heterogeneous. And when you look at a very simple random graphs model like the Erdős-Renyi one, you don't capture this heterogeneity. So a very simple way, at least for a statistician, to capture heterogeneity is to assume that you have a group structure on your individuals. So that's a very natural idea. And if you want to do a classification of the nodes, that's also interesting, because it will induce a summary of the information that is contained in these nodes. And so you can summarize your data set into very few different behaviors, let's say. So that will lead us to the stochastic block model. And one other motivation or justification that we could mention for using the stochastic block model is given by the Meredi regularity lemma, which roughly says that every large enough graph can be divided into subsets of about the same size, so that the edges between these different subsets behave almost randomly. So that's really what the stochastic block model does. The only cheating part here is that in this regularity lemma, you have no idea of what's the number of blocks that you should use to model this data. And in practice, if it's too large, then it can be useless. Okay, So last thing I want to say about in this introduction is that when should you do a nodes classification and why should you do that? So first of all, I'd like to mention that the practical methods that I will discuss here are really suited for graphs that are not too large. So not those data sets like the internet or the web page that we heard this morning about. So when I say not too large, it means with up to a few thousands of nodes. And why is that? Because we will rely, for instance, on variational approximation methods that even if you can speed them up, maybe they are designed primarily not to work with very large data sets. And another very important reasons, and maybe most of the people, well, some people here might not agree with me on that point, is that I am not completely convinced that node classification is a good idea if you have a very large data set. Because if you're a statistician and you're doing node classification, it's, as I said, to summarize the information in your data set. And if you need, like, I don't know, 50 groups to summarize that information, that's already too much, okay? You can't look at 50 groups. Or you will look at peculiar groups and say, okay, on that group I recognize this behavior. But then maybe you are finding something that you already know a priori. So, okay. But this might be controversial, and maybe not everybody will be okay with me on that point. Okay, so again, the stochastic block model. Very briefly, because we've discussed that a lot of time now. In the parametric case, you observe a graph. Here I put some colors on the nodes, and you don't observe the colors. But what you observe is the edge distribution between those nodes. And you assume that you have k groups. So here the groups are represented by those colors, and so you don't observe these groups. So you have these latent random variables Zi, which are assumed to be IID, with a multinomial distribution with a parameter pi among these k groups. So Zi is not observed. This is my latent random variable. And what I observe is the presence or absence of an edge, which I denoted here by Aij between node I and j. And well, in the stochastic block model, you just simply assume that conditional on the Zi's. So if you knew the latent configuration, then the random variables would be independent, and with distribution, a Bernoulli distribution with a parameter gamma that only depends on the colors of the nodes that you are trying to link. So this Zi and Zj. And people work a lot with the stochastic block model in binary graphs, but most of the graphs that you encounter in real life are weighted. And so it's very easy to generalize the stochastic block model to the weighted context. And well, a very simple way of doing that is for the latent variables, you don't change anything. These are still IID random variables taking k different values with some probability pk. And what you observe now, I call them weights, but you don't need them to be positive unless you're doing spectral clustering. It's of no importance that the value that you put on the edge between IIG is positive. It can be anything, but sometimes you want to have true zero values. So if your IIJ is, let's say, anything like a vector or a Gaussian random variable, if you put Gaussian random variables, then you won't have true zeros, and so your matrix will be completely full. And sometimes you want that two individuals don't interact at all. So a way of doing that very simply is to say that the conditional distribution of your edges Aij, your weighted edges, conditional on the latent variables, you put a mixture of direct distribution at 0. So that's for the non-presence of an edge. This happens with this parameter gamma 1, which is the sparsity of the graph. This can depend on the groups you are looking at. And there's a second distribution here. Let's say it can be Poisson. If it's Poisson, you have to remove the 0 value on your Poisson distribution just to get no problems here of identifiability. It can be an exponential distribution. It can be a Gaussian one, anything you want. Okay? So that's really the parametric version of the stochastic block model, where you don't just put one edge, you put any value on the edge that you model through a parametric distribution. Okay, the first thing I want to really make clear is that SBM classification, for me, it's really different from community detection. And to illustrate that, I've drawn this very toy example. This is really a toy example. On this graph, if you do community detection, then you will end up with these two clusters, one red cluster and one blue cluster, and these are separated like that. If you do SBM clustering, then you can recover this type of cluster, meaning that you will put these two nodes within the same group because they behave similarly. They are hubs in the networks. And those blue nodes, they are all in the same group because they behave similarly. They are, let's say, peripheral nodes in your network. And this kind of structure, you cannot obtain it with community detection. So that's really a difference that exists between SBM and community detection, but you can obtain this kind of classification with SBM too. So SBM encompasses community detection. There are many particular cases and generalizations that you can do about the stochastic block model. So the one that we just discussed, if your matrix of connectivity parameters gamma has one value on the diagonal and another value outside the diagonal, and if the value on the diagonal is much larger than the value outside the diagonal, then you go back to community detection. Otherwise, you will find disassortativity structures in your graph if it's the converse, alpha much smaller than beta. And the people developed a lot of generalizations. We've heard a lot about that yet. Overlapping groups, including covariates, degree corrections. You can also consider latent block models where, in fact, you're not looking at an adjacency matrix that is a square matrix. You're looking at bipartite graphs, for instance, and you encode this data into rectangular matrices where the individuals on the rows are not the same than the individuals on the columns, and you want to consider the interactions between two different entities and two different sets. Of course, the non-parametric SBM, also the graphon and dynamic versions. And if you're interested in dynamic versions of the stochastic block model, then you should probably come back in December for the last workshop that is dedicated to dynamics. Okay, so now I come to the core of my talk. I want to discuss these statistical issues. And the first one I've been really interested in is identifiability. So we've discussed the identifiability issue for the graphon so far, but we never discussed yet this week identifiability problem for the stochastic block model. And well, obviously, when you have this kind of latent group models, you can only identify the parameters up to a permutation on the group's label. That's very well known. So you would say that the parameter theta here, that's the group proportions and the connectivity matrix, it is identifiable whenever two distributions are equal if and only if there exists a permutation on the K groups such that pi and gamma are in fact the same up to this relabeling of the groups. Okay? But whether one may uniquely recover the parameters up to a permutation is a delicate task. So you know that you can't go behind the permutation, but whether you will always obtain that, that's not obvious, it's delicate, And well, there's an obvious necessary condition that tells you, if you look at the connectivity matrix, this gamma here, any two rows or any two columns of this connectivity matrix must be different. So a row of this connectivity matrix tells you, oh, a specific group will connect to the other ones. And if two rows are equal, it means that two groups have exactly the same behavior with respect to the other groups. And so these two groups are the same. You can collapse them. So this is a really necessary condition. It's obvious that you require that at least. But is this sufficient? And the answer is no. Not in general. There's no general proof of this being sufficient. So I'm going to explain what are the different identifiability results that we've got so far. It started with a paper with Elizabeth Allman and John Rhodes and myself, where we studied the stochastic block model with only k equal 2 groups. And in this very specific case, on the binary version, we could prove that as soon as these three parameters, these connectivity parameters, are distinct, then you obtain identifiability of the model, and you would require the distribution over 16 nodes. That's sufficient. Okay, but that was only binary SBM for only two groups, which is a very, very specific case. We generalized that in another work to binary SBM with more than 3 groups, and in fact we also did works on the weighted version. I'm not discussing that yet. So for the binary stochastic block model with more than 2 groups, we proved the result of generic identifiability, which means that we said, okay, there's a subset of the parameter set where the parameters might not be identifiable, but this subset, that's a variety, and so it's small. And in particular, it has Lebesgue measure 0 on your whole parameter set. So in general, you will obtain a data set which has an identifiable parameter, so no problem. And the condition here was not explicit, so we did not describe the variety where problems could happen. There's another very interesting result for the directed binary stochastic block model by Celis and co-authors that proved that if you consider your connectivity matrix gamma and you multiply it by the vector of proportions p, then if it has distinct coordinates, you can establish identifiability that's sufficient. But this condition, it's not implied by the preceding one. Okay, so that's an additional condition which is explicit in this case, and it's really in the binary context. And for weighted SBM, the problem is harder because for the binary you have the set of equations that define your probability distribution, so you can analyze them. But in the weighted case, things are more complicated. And the only known results that we have in this paper requires that all parameters in your connectivity matrix are distinct. So this is really a very stringent condition, and we don't know if it's necessary or not. So that's really an open question. Do we really need this extra condition? Is the condition on 2 rows or 2 columns being different sufficient or not? Okay, now I'll discuss parameter estimation. So the one interesting goal could be the MLE, the maximum likelihood estimator, and well, just to state things clearly, the likelihood computation is untractable here unless for small values of n. And so what you do in this context, when you have configurations, latent configurations, that is a too huge space to sum over them to compute the likelihood, you use EM algorithm. So EM algorithm, that's for expectation maximization. And in practice, you can apply it whenever you know how to handle nicely this conditional distribution of your latent random variables given the observations. And here in our stochastic block model context, this distribution is not factorized. And the fact that it is not factorized makes it harder to put a finger on it, and so you cannot do EM algorithm exactly on this context. So what do? There are many alternatives. We've heard Thiago talking about Gibbs sampling yesterday. I will discuss variational approximation to EM algorithm, and in some very specific case you also have ad hoc methods like composite likelihood or moment methods or degree methods. So the variational approximation, Peter already explained that very well yesterday, but let me just give you a brief recap of what it is. So you have the log likelihood of the observation. That's the logarithm of the probability of your observation for some specific parameter value. And with a simple trick, you can write it in that way, what we call the complete log likelihood minus the logarithm of the distribution of your latent random variables given the observations. And now you take any distribution Q on your random variable Z, and you take expectation of this equality with respect to Q, and the left-hand side doesn't change because it doesn't depend on Z. And on the right-hand side, you obtain the expected value under Q of this complete log likelihood. And these things, you can show very easily that it's just the entropy distribution of Q plus the Kullback-Leibler divergence between Q and this posterior distribution of the latent given the observations. So expectation maximization principle is very simple. You iterate two steps. The first step, the E step, is to maximize this quantity with respect to Q. And when you do that, since on the left-hand side it doesn't depend on Q, maximizing this with respect to Q is equivalent to minimizing this Kullback-Leibler divergence. And so the solution is to take Q equal to the probability of the latent random variables given the observations. And on the M step, you keep no Q fixed, and you want to maximize this quantity with respect to theta now. And you update it to the parameter value theta t plus 1, which is the maximizer. And now this is completely equivalent to maximizing this conditional expectation. Since this entropy does not depend on theta, this is equivalent to maximizing this conditional expectation over Q of this complete log likelihood. So that's really EM algorithm. And in the variational version of EM algorithm, since you cannot do this step exactly, meaning you cannot choose Q to be equal to this distribution because this distribution is too complex, it has not a factorized form, then you decide, okay, I will go for an easier job. I will search for an optimal value of Q within a restricted class of distribution. And I take for this restricted class the class of factorized distribution. Okay, and then I choose at the E step the best factorized distribution that approximates this conditional distribution that I don't know with respect to the Kullback-Leibler divergence. And okay, summing up, what happens here is that finally, if you look at the log likelihood of your observation, it's lower bounded by this quantity, and you are optimizing this lower bound on the log likelihood of the observations. And as Peter said yesterday, it might not be a good idea, or at least you could wonder why it works, because optimizing a lower bound of your quantity of interest does not make sense in general. Okay, I mentioned very briefly, because I think I'm already late.
No, we started 5 minutes late.
Yeah, okay.
Another 7 minutes.
Okay. If you want to do model selection, then the answer depends on whether you are a frequentist person or Bayesian person. If you're a frequentist person, as I am, then you cannot rely on maximum likelihood, so you cannot have IIC or BIC criterion, but you can use what we call integrated complete likelihood, which is mostly you just rely on this quantity at the very end of your algorithm and you penalize it by the number of parameters in a certain way. So that's a bit like criterion, except that you don't use the likelihood. And in a Bayesian setting, Neil has a very nice paper on MCMC approaches to select the number of groups. And recently, Combe and Latouche came up with exact version of the ICL on a Bayesian setting, and it requires greedy search optimization, and that's very, very promising. Okay, very quickly, some convergence results. The first question I asked myself when I worked on this stochastic block model is, why does the variational approximation work so well? Because, okay, I shouldn't say that because Peter said yesterday that it wasn't working, so maybe I should have changed this part of the talk, but you know, we had the conference dinner yesterday, and then I didn't want to go through my slides again, so really sorry. So in practice, it happens that the variational approximation works, okay? And it shouldn't. And there's a very, very nice paper by Gunnar, Wardana, and Byrne that says variational approximation does not converge to a maximum likelihood estimator unless the true posterior is degenerate. So how come? And in fact, it turns out that this is the case in the stochastic block model. In some sense, this posterior distribution, when you look at the distribution of the latent random variables given, oh, this should be an A, sorry, this should be the adjacency matrix. This is degenerate in the sense that it converges to a product of direct distributions. And there are also very nice results from Alain Celis and Peter Bickel that he mentioned this yesterday. In fact, variational EM estimators, we can prove that they are asymptotically equivalent to the MLE, and the MLE is convergent and asymptotically normal. And I believe Ari talk this afternoon will also present minimax rates in the graph setting, so I don't discuss this part more. Okay, the very last thing I want to discuss is what shall we do when we want to analyze dynamic networks. The first thing, the first problem I've encountered recently is the problem of aggregation of data versus streamlinks. I'll talk of the streamlinks just after. First, aggregation. So most of the dynamic networks that you encounter, they are constructed by aggregating data over pre-specified time intervals. So for instance, with the animals dataset, we looked at either the day time interval or the season time interval, and we construct the data sets by aggregating the number of interactions of the individuals over these windows, predefined windows. And the question is, how should we choose the window size? That's an important question. So there are some answers, and in particular, I very much like the answers by Raimonda, Sulo, Caceres, and co-authors in these two papers. So the idea that Raimonda proposed is, okay, you just fix an objective. So for instance, say you want to do link prediction. Then you will look at all the possible window size, do the aggregation on this window size, and look at the link prediction algorithm with which window size do you do the best job. Okay, so that's one possible answer, and in fact you can choose many different criteria and do that. Okay, the problem is that it's computer intensive, and if you are doing simple statistics, you might not have any idea of what you are trying to optimize. Okay. So maybe you don't want to do link prediction, maybe you don't want your graphs to be clustered, so you don't want to optimize the modularity. So then how do you choose this window size? So one of the questions I'm currently thinking of is what are the possible approaches to select those window size, and can we quantify what we are losing by aggregating data, because I believe we are losing something. And I just mentioned that I've done some work on a dynamic SBM model with aggregations, and we had talks on that. I think it was Wednesday, and there are many proposals. I just cite two of them here. The main issue, as we saw on Wednesday, is to decide whether you want the groups to change with time or the connectivity parameters to change with time, or both. And if you want to change both, then you very quickly realize that it's not possible without restrictions. So you need to add restrictions on the model in order to get identifiability. So we have a proposal of a restricted model where both connectivity and groups can change with time, and it remains identifiable. And okay, the other point of view that you could have on these graphs, on these dynamic graphs, is instead of aggregating data, you just look at stream links. So stream links, they record the interactions between two individuals, I and J, at some time point t. So let's say you have a data set of phone calls or email exchange. Then you know that at some time point tm, these two individuals, IM and GM, had an interaction. So you don't want to aggregate that over time intervals. You just keep the data in its raw form like that. And the idea is that now the simplest way to view that is to look at the counting process of the interactions between I and J up to time t, and you look at this in a continuous time framework. So you don't aggregate it, okay? And so you're working with point processes, and there are some works in particular on the OD data. So OD data, these are data of origin destination flows of individuals between two different geographical points. There are works that clusters these point processes, but if you cluster them very simply, yeah, I know I need to stop. If you cluster them very simply, then you will have groups on the pairs of interactions. So maybe it's wiser to cluster the individuals. And we've done recently a work where we have a dynamic version of the stochastic block model, but for these point processes. And the questions, very briefly, we don't have graphs anymore when you look at stream links, and we could ask, okay, are we losing something? At least the visual representation is an issue, and this thing of the point processes, they are not suited for interactions that last over some time interval. So if you are looking at phone calls and you want to say, okay, these two persons, they interact between this time point and this time point, then it's not obvious how you will model that with point processes. And that's all. Thank you for your attention.
Personally, I feel that, I mean, I've seen this motivation for the block model in terms of Semmeradi's lemma a couple of times, and personally I feel we should be very careful with that.
I agree.
Because if you actually compute the constants in Semmeradi's lemma, then you find that actually the number of particles in the universe is not all that large.
Yeah, I completely agree.
And that kind of regularity is not what we see in a block model, right? What we see in the block model, if anything converges, is probabilistic concentration, and that's a really completely different thing.
Okay, I'll remove it.
Yeah, I just, I don't know that we differ so much on whether it works or not. The trouble is, there's the, how well the theory works, and the theory tells you indeed that in this range, the true maximum behaves nicely.
Yeah.
The problem is finding it, and actually, as you said, in some cases you can find it easily, in others you cannot.
So I did not discuss initialization of those algorithms, but that's really a critical issue. I agree. Yeah.
Well, I think we're running a little bit behind. If you have more questions, we'll have lunch following up. So let's thank Catherine again.